Okay, so now we're going to revisit Green's theorem. And we proved the flux form of Green's theorem a few lessons ago. So let's actually just remind ourselves what it says. If this is a unit tangent vector, then I can define my unit normal vector. And so this is just a two-dimensional vector field. And this is, so it would be helpful, yeah, this is just in the xy plane. Okay, so if I parameterize the curve, then I can find my unit tangent vector. That's just going to be the velocity divided by the speed, so I'll just write it in vector form. So it's just the velocity divided by its magnitude. And then to get the unit normal vector, we rotate that 90 degrees such that it's always pointing to the right of the curve as we're moving along. And so that's equivalent to taking the I and j components, swapping them, and making one of them negative. And so in order to make it always point to the right of the curve, we're going to make the second component negative. And we will still have the same magnitude, so you're still dividing by this. And you can check that these are normal. Just take the dot product between them and you'll notice t dot n is in fact 0. Okay, now what we're going to do is we're going to apply Green's theorem to a random vector field G, and we're going to define that vector field to be some function q for the I component and then some function negative p for the j component. So let's recall Green's theorem's flux form told us that if we wanted to calculate the flux, that it's equivalent to integrating the divergence everywhere on the interior of the region. Where I'm defining the interior, this is my interior region R, and C is the boundary. Okay, so let's actually write out what this means in terms of our particular vector field G. This means and we'll actually do it to actually evaluate it. We change variables and we write everything in terms of T. So let's imagine that we've substituted in for G to write it in terms of T. I'm just going to still write it as Q negative P, but you can assume I'm meaning we're going to have those in terms of T now. And then we're dotting this with the normal vector, so I'm just replacing this with the normal vector. And then I need to rewrite ds using the Jacobian, so my tiny little distance is the same as my speed times a tiny little time. And so that's just rewriting the left-hand side, and now we can rewrite the right-hand side because we can actually calculate the divergence of this vector field. Recall, it's going to be the partial of the I component, so in that case it's the partial of q with respect to x, and then plus the partial of the j component with respect to y, but my j component is negative p, so this is going to become minus partial of p with respect to y. So this is a theorem. This is just applying a theorem we already know to just a random vector field G, where G has this particular form. Let's actually now write out a little bit more. So let's actually do the dot product. Up here I'd get q dy dt plus p dx dt over the speed, and so I'm just going to rewrite it in a slightly different order, and I'm going to put different colors because I'm hoping you notice something cool about when we actually evaluate this. So I'm not changing anything, I'm just doing it in a slightly different order. And then we have q dy dt divided by the speed, and then we still have the speed dt. And this is equal to the same thing on the right hand side, so I'm just going to rewrite that. And now I want you just to look really carefully and tell me if you notice how we could rewrite this first integral on the left now in terms of f and t. I tried to make it pretty obvious the way we wrote it. But if you look closely, you realize, wait, this is exactly the same as the dot product between the vector field f and the unit tangent vector. And this is still just ds here. And my right-hand side, wait, we've seen this. In fact, we saw this on the previous page in our previous example. This was actually just the k component of the curl of a vector field f if we define the vector field f as p I q j. And so this is actually giving us a new form of Green's theorem. Because we proved this up here for any vector field G of this form, and we get to this conclusion that for any vector field f, this following relationship holds, then this can be generalized. And this is what we call Green's theorem, the curl circulation form, because now notice this left side right up here is telling us that if we want to find the circulation, F dot T, around the boundary of some curve C, then it's going to be equivalent to integrating the K component of the curl over the interior. So this gives us a really cool interpretation of the K component of the curl, which I was talking about in the last page. I said we'll come back and get an interpretation. We can think of this as like a circulation density, because when we add it up everywhere on the inside, we get the total circulation around the boundary. And again, this is only going to hold if your vector field has continuous partial derivatives everywhere throughout your region, because as we looked when we were describing macroscopic versus microscopic circulation, we noticed that we could look at microscopic circulation, which is really like what the curl was capturing, like how much, these are supposed to look like little arrows of how much something's rotating, and we could look at how much something is, your vector field's causing like a paddle wheel to rotate around the interior, and eventually that needs to match with what's actually happening on the boundary as long as your vector field's continuous. And another piece of another intuitive way to think about this is just like when we proved this with flux, we could take this little interior region, chop it up into a bunch of little rectangles. So let me just give you like one little rectangle here and another little rectangle here, and we could calculate the circulation around one of these rectangles, and then we could add it to the circulation around another one of these rectangles. And notice we're going to get cancellation again on the boundary, because the line integral along the boundary will be going up on the left rectangle and down on the right rectangle if I'm trying to go counterclockwise for both. And so it's the exact same idea that we saw with flux, where I can add up basically what's happening with the circulation on the interior, and I'm going to end up getting the total circulation around the boundary. Now, just to be clear, what I'm really adding up on the interior is the circulation density, because it's going to have units of circulation per unit area, the dA there, and that's why when I add them up on the inside, multiply by the areas of one of those tiny little rectangles, I'm going to get the total circulation around the exterior. One other thing I'd like to show you is the other way you might see this theorem written, and I'll just do it down below. It's just shorthand for this. It's the exact same idea, but oftentimes you'll see that instead of doing F dot T, they'll come back up here to our dot product version, and we'll write it as P dx plus Q dy. It's just shorthand notation, so it doesn't mean anything until you actually change variables and put everything in terms of T. But that's coming from this region. I don't even know how I can highlight this for you. I think I'll just do it here. It's coming from this up here. It's just a shorthand for that. And sometimes you'll see this, and then the right hand side, sometimes we'll actually write out the curl, and so we'll write it just like we had it up above, which was partial of Q with respect to X minus partial of P with respect to Y. And let me clarify, this is not just the curl, this is the K component of the curl, which is really measuring the scalar rotation speed of a little paddle wheel on one of these little infinitesimal rectangles. All right, so let's do some examples and see how we can use this. The good news is this is going to give us another way to calculate circulation. Instead of just doing the line integral, we can now do a double integral on the interior.